Somewhere in your backyard right now, there is enough room to build a machine that can show you galaxies 25 million light years away. And most people will never know it because they think that kind of power costs a fortune. Tonight I am going to prove that wrong 3 times over, because I actually built 3 backyard observatories, one for $500, one for $5,000, and one for $50,000. And what happened when I pointed all 3 at the same patch of sky is going to change the way you think about stargazing forever. If you have ever stood outside on a clear night and looked up and felt that pull, that quiet ache to see more than your eyes alone can give you, then you already understand why people spend their savings chasing photons from stars that died before humans existed. The question everyone asks me is simple. How much do I actually need to spend to see something real? Not a blurry smudge, not a grainy phone photo, something real. So I decided to stop guessing and start testing. And over the next hour I am going to walk you through every wire, every mount, every lens, and every mistake I made building 3 completely different backyard observatories from the ground up. By the end of this video, you will know exactly what your money buys at each price point. You will know which budget actually makes sense for your goals. And you will understand why some of the most breathtaking views of the universe do not require a mortgage, while some of the cheapest gear can leave you staring at a fuzzy gray dot, wondering what you did wrong. Stick around, because Tier 2 surprised me in a way I did not expect, and Tier 3 revealed something about the sky that even professional astronomers do not get to see very often from their own backyard. Let us start at the very beginning with the $500 build, because this is where almost everyone starts, and this is where most people either fall in love with astronomy or give up on it forever within the first 2 weeks. Part 1. The $500 Observatory. When people imagine a budget telescope, they usually picture something flimsy, something that wobbles in the wind and shows nothing but a white blur no matter what you point it at. That reputation exists for a reason, because a huge percentage of entry-level telescopes sold in big box stores are genuinely bad instruments wrapped in exciting box art showing photographs that the telescope itself could never produce. So the first rule of the $500 tier is this. You are not buying a telescope. You are buying an entire system, and the smartest way to spend that money is almost never on the biggest tube you can find. I started with a 6-inch tabletop Dobsonian reflector, and I want to explain why that specific design matters so much at this price point. A Dobsonian mount is essentially a simple rocker box, no motors, no computer, no complicated counterweight system. You point it with your hands, and that simplicity means almost none of your budget goes into mechanical complexity. Instead, nearly all of your money goes into the one thing that actually determines what you can see, which is aperture. Aperture is the diameter of the main mirror or lens, and it is the single most important number in all of amateur astronomy because a wider aperture gathers more light, and more light means fainter, more distant objects become visible. With a 6-inch mirror, which is about 150 millimeters, you are already collecting roughly 600 times more light than the naked human eye. That sounds abstract until you actually use it. On my first clear night with this $500 setup, I pointed it at Saturn, and even a beginner telescope at this aperture will show you the rings as a distinct, separate structure around the planet, not just an oval blob. I remember hearing genuine gasps from neighbors who wandered over because they assumed a picture like that required a much more expensive setup. But building a $500 observatory is about more than just the telescope tube. I allocated my budget roughly like this. $280 went to the tabletop Dobsonian itself. $60 went to a proper sturdy tripod stand, because tabletop scopes without a stable base are miserable to use. You end up hunched over a picnic table fighting your own back for every observation. $50 went to a SkyMap app subscription and a basic planisphere, the old-fashioned rotating star wheel that still works perfectly without batteries or a phone signal. $40 went to a red flashlight, because white light destroys your night vision, and it takes nearly 30 minutes for your eyes to fully adapt to darkness again after exposure to a bright phone screen. The remaining $70 went into 2 additional eyepieces beyond the stock ones that come in the box, because stock eyepieces are almost always the weakest link in a budget telescope package. Setting this observatory up for the first time took about 20 minutes, and that is actually one of the biggest hidden advantages of the $500 tier. There is no polar alignment procedure. There is no computerized go-to system to calibrate. You carry it outside, you set it on a flat surface, and within minutes you are observing. For someone brand new to astronomy, that low friction matters enormously, because the telescope that gets used every clear night beats the telescope that sits in a closet because setup feels intimidating. Here is what this budget tier actually delivered under real dark sky testing. The moon looks spectacular, with crater shadows sharp enough to see the Terminator line, that boundary between lunar day and night, crawling slowly across the surface in real time if you watched long enough. Jupiter showed 4 steady points of light, the Galilean moons, arranged in a changing pattern night after night exactly as Galileo himself first documented centuries ago. Saturn's rings were clearly separated from the planet's disk. The Orion Nebula appeared as a soft greenish-gray cloud with a small cluster of young stars embedded inside it, visible even under moderate light pollution. What did not work well at this budget? Deep sky objects beyond bright nebulae and star clusters were disappointing. Distant galaxies appeared as faint smudges at best, and under anything other than genuinely dark skies far from city lights, many targets were simply invisible. Photography was essentially off the table. You could hold a phone up to the eyepiece and capture something recognizable of the moon, but planets and deep sky objects were far too dim, and the mount too unstable for anything resembling a real astrophotograph. The $500 observatory is, in my honest assessment, an extraordinary entry point. It teaches you the sky. It teaches you patience. It teaches you to find objects manually using star charts, a skill that genuinely deepens your understanding of the night sky in a way that automated systems sometimes shortcut. But it has a hard ceiling, and once you hit that ceiling, the next question becomes obvious. What does 10 times the budget actually buy you? Part 2. The $5,000 Observatory. This is where things get genuinely interesting, because $5,000 is the tier where amateur astronomy transforms from a hobby of looking to a hobby of capturing, and that shift changes everything about how you interact with the night sky. For this build, I moved to an 8-inch computerized Schmidt-Cassegrain telescope on a motorized equatorial mount, paired with a dedicated astrophotography camera, rather than relying on eyepiece viewing alone. Let me break down where the money actually went, because the allocation here looks completely different from the $500 tier. The telescope optical tube itself was around $1,800. The computerized go-to equatorial mount, which tracks the sky automatically by compensating for Earth's rotation, ran approximately $1,500. A dedicated cooled astronomy camera, which is far more sensitive to faint light than a standard DSLR, cost about $1,100. The remaining $600 covered a light pollution filter, a laptop running capture software, cables, a portable power station, and a proper carrying case. Because at this weight and complexity, you do not want to be improvising transport. The single biggest change at this tier is tracking. Earth rotates constantly, which means without active tracking, any object you observe slowly drifts out of view within seconds, and long exposure photography becomes completely impossible because stars smear into streaks. The equatorial mount in this build uses a motor aligned with Earth's rotational axis, so once properly polar aligned, it counteracts that rotation and keeps a target locked in the same position in the eyepiece or camera sensor for hours if needed. That single capability is the difference between seeing Saturn's rings and photographing Saturn's rings, with visible cloud banding on the planet itself. It is the difference between glimpsing a faint gray smudge that might be a galaxy and capturing a genuine image showing spiral arms, dust lanes, and background stars scattered like glitter behind it. Setup at this tier took considerably longer, roughly 45 minutes including polar alignment, which involves precisely orienting the mount toward the celestial pole using either a built-in polar scope or an automated alignment routine guided by the mount's onboard computer. The first few times I did this, it took closer to 90 minutes because polar alignment has a real learning curve, and getting it wrong does not ruin your night, but it does degrade tracking accuracy over long exposures. Once operational, the results were dramatic. I captured the Andromeda Galaxy, our nearest large galactic neighbor sitting roughly 2.5 million light-years away, and after stacking multiple exposures in processing software, the image clearly showed its bright core and the beginning of its spiral structure, something completely invisible through the $500 setup from the same backyard. The Orion Nebula transformed from a soft gray smudge into a genuinely colorful image showing pink and orange hydrogen emission regions, structure that the human eye simply cannot perceive in real time because our eyes are not sensitive enough to see color in faint light, but a camera sensor collecting light over several minutes absolutely can. Saturn through this system, viewed live on a laptop screen with the camera in high frame rate planetary mode, showed the Cassini division, the dark gap separating Saturn's rings, along with subtle banding on the planet's atmosphere. Jupiter revealed the Great Red Spot as a distinct oval feature, along with multiple visible cloud bands rather than just a flat orange disk. This tier also introduced a new challenge that the $500 build never presented, which is post-processing. Raw astrophotography data straight off the camera sensor looks disappointing, often dark, noisy, and unimpressive. The actual image only emerges after stacking dozens or even hundreds of individual exposures using specialized software, aligning them, and carefully adjusting contrast and color to reveal the faint detail buried in the noise. This adds a genuine skill requirement on top of the observing itself, and honestly, for some people this is where the hobby becomes even more rewarding, because you are not just observing the universe, you are actively processing and revealing structure that raw human vision could never access. The $5,000 tier is, in my assessment, the sweet spot for serious hobbyists. It delivers dramatically more capability than the $500 tier, roughly proportional to, but arguably exceeding the 10 times increase in cost, because the addition of tracking and imaging unlocks an entirely different category of target, not just brighter versions of the same objects. But it also demands real-time investment in learning polar alignment, capture software, and image processing, and it introduces genuine technical failure points, like guiding errors, condensation on optics, and cable management issues in the cold, that a simple Dobsonian never has to deal with. So what happens when you multiply the budget by another 10? Does $50,000 deliver another proportional leap, or does the law of diminishing returns finally catch up with the night sky? Part 3. The $50,000 observatory. This tier is where backyard astronomy stops resembling a hobby and starts resembling a small research installation, and building it fundamentally changed how I think about what an amateur can actually accomplish from their own property. At the center of this build sits a 14-inch premium optical tube, a research-grade instrument with optical quality that rivals equipment used at small university observatories. Around it, I built an actual permanent structure, a roll-off roof observatory shed, essentially a small building on a fixed concrete pier with a roof section that slides completely away on rails, exposing the telescope directly to the sky without ever needing to carry equipment outside or realign anything from scratch. Here is the rough allocation across this budget. The optical tube itself accounted for roughly $12,000. A premium research-grade equatorial mount, engineered for extreme precision tracking over many hours with minimal periodic error, came to approximately $15,000. The permanent pier and roll-off roof structure, including concrete foundation work and the automated roof mechanism, cost around $11,000. A specialized cooled monochrome imaging camera paired with a filter wheel holding narrowband filters, which isolate extremely specific wavelengths of light emitted by hydrogen, oxygen, and sulfur in nebulae, added roughly $7,000. The remaining $5,000 covered an automated focuser, a guide scope and camera for correcting tiny tracking errors in real time, weatherproofing, remote control computer equipment, and a dedicated all-sky camera that monitors cloud cover and can automatically close the roof if weather rolls in unexpectedly. The permanence of this build changes the entire relationship with observing. There is no more 45-minute polar alignment ritual every single session. The pier is fixed in place, precisely aligned once during construction, and it stays aligned indefinitely. On a clear night, opening the roof and beginning an imaging session takes under 5 minutes. This alone transforms behavior. At the $500 and $5,000 tiers, marginal nights, ones with some haze or only a short window of clear sky, often get skipped because setup effort does not feel worth it. With a permanent observatory, those marginal nights become easy opportunities, and total observing hours per month increase dramatically simply because the barrier to starting is nearly eliminated. The imaging results at this tier moved into genuinely different territory. Using narrowband filters and the monochrome camera, I captured a detailed image of the Eagle Nebula, showing the famous pillars of creation structure, the same dust columns made famous by space telescope imagery, resolved with visible internal structure and texture, not just a vague bright patch. The Whirlpool Galaxy, roughly 23 million light-years distant, showed clear spiral arm structure along with its smaller companion galaxy, captured with enough resolution to see individual bright star-forming regions within the spiral arms themselves. Perhaps the most striking difference at this tier was in faint, extended targets that are essentially invisible at the lower budgets. The Veil Nebula, the delicate remnant of a supernova explosion that occurred roughly 10,000 years ago, appeared as intricate wispy filaments of ionized gas stretching across the frame, an object that produces essentially nothing visible in a $500 telescope, and only a faint hint of structure at the $5,000 tier. I also want to be honest about something, because a fair comparison has to include the downsides. The $50,000 observatory required real construction knowledge, permits in my local jurisdiction for the permanent structure, and ongoing maintenance, including motor lubrication, weatherproofing checks, and periodic professional collimation of the massive optical tube. Software complexity also increased substantially, with automated sequencing, guiding, and roof control systems that took weeks to fully configure and troubleshoot. This is not a beginner instrument, and frankly, it is not even purely a hobbyist instrument. Several amateur astronomers running observatories at this tier contribute their imaging data to actual scientific research, including monitoring variable stars, tracking near-Earth asteroids, and even contributing supernova discovery confirmations to professional astronomers. The head-to-head comparison now let us put all three side by side, because the real value of this experiment is not any single build. It is understanding exactly where your money produces the biggest jump in capability, and where it starts producing diminishing returns. Going from $500 to $5,000, a tenfold increase, produced what I would call a categorical leap. You gain the ability to track objects for extended periods, which unlocks astrophotography entirely, which unlocks color, faint detail, and dramatically fainter objects that are simply not accessible through eyepiece observation alone regardless of aperture. This jump fundamentally changes what kind of hobby you are practicing. Going from $5,000 to $50,000, another tenfold increase, produced a significant but proportionally smaller leap in raw visual spectacle, and a much larger leap in convenience, precision, and access to genuinely faint, extended, scientifically interesting targets. The moon, planets, and bright popular targets like the Orion Nebula look impressive at the $5,000 tier already, and the $50,000 tier refines and sharpens those images rather than transforming them entirely. Where the top tier truly separates itself is on the faintest, most delicate structures in the sky, supernova remnants, distant faint galaxies, and subtle nebular detail that essentially do not exist as viewable targets at the lower tiers at all. If I had to summarize the entire experiment in one sentence, it would be this. The first 10 times your budget buys you a new hobby, and the second 10 times your budget buys you a research instrument. For most people watching this, genuinely, the $5,000 tier represents the strongest value relative to cost, delivering roughly 80% of the emotional and visual impact of the $50,000 system at 10% of the price, and without requiring a permanent structure or specialized construction knowledge. The $500 tier remains the correct starting point for nearly everyone because it teaches core skills, costs little enough that walking away carries minimal risk, and still delivers genuinely stunning views of the moon and planets that surprise almost everyone who tries it for the first time. The $50,000 tier is not really a beginner upgrade path at all. It is a destination for people who have already fallen deeply in love with this hobby and want to push toward genuinely research-grade capability from their own backyard. Whatever budget you are working with, the most important takeaway from everything I tested is this. Every single one of these 3 observatories, even the cheapest one, showed me something that most people on Earth will never see with their own eyes: the rings of Saturn, the moons of Jupiter, a nebula that gave birth to new stars. The sky does not actually require $50,000 to be breathtaking. It requires curiosity, a few clear nights, and the willingness to step outside and look up. If this comparison helped you figure out where to start your own astronomy journey, let me know in the comments which tier you would build first. And if you want to see the full step-by-step build guide for any of these 3 observatories, including exact part lists, subscribe and stay close, because that is exactly what is coming next on this channel.